Hello, candidates. Very good evening to everyone. I hope I'm audible. Can anyone please confirm me in the message box? Am I audible to everyone or not? Let me just share my screen. Hi, Hemant. Hi, Spurti, Santla, Hitashri, Sneha, Sarath, and the rest candidates. Guys, I have already shared my screen. Just quickly let me know am I audible and my screen is visible, right? You can further continue. Got it, Sneha, right? Okay. So, guys, in the previous classes, we have already covered the part that was related to the bagging and boosting, right? And it was a complete part of ensemble technique, right? Which was very important for the interview point of view. On today that we are going to start the rest part of the ensemble technique, that was like the boosting part, right? But before directly starting the boosting part, we have to understand some sort of concept. Then we can probably understand the boosting part, right? So let's just start with the technique. The problem that we generally face while training the module or like while training the model is that overfitting and the underfitting, right? So today we are going to discuss overfitting, underfitting, and boosting techniques. Okay. So let me just share this notebook with all of you so that you can you can practice it parallelly, right? Okay. I have also given you some sort of project candidate, the project was related to, I think, heart disease classification, heart disease prediction, and the first was to predict the fuel efficiency of auto MPG dataset, right? How many of you have already completed that one? Just let me know in the message area. Okay. So this is the notebook that you can use it for today practice. Okay. So guys, whenever we train model using machine learning technique, now we generally face a problem, and the problem is like underfitting problem and the overfitting problem, right? So let's just first understand what is the use of like concept of all these technique: overfitting problem, underfitting problem. Okay, so overfitting is a problem, like it is a problem in ML where our model trained well on training data set, training data set, but or giving good accuracy or score on training data set, but not performing well with testing data set. So this is a problem in the ML, right? It's like we have created a model. The model was performing well on training data set. Whatever the data set that we have, we particularly picked, we simply converted or like split the data into training and testing part. Then we trained our model, right? If our model performing well on training side, it's like getting accuracy of 100% on training side, but when we test our data, we are not getting the good accuracy, we are not getting the good score. In that case, we generally say a problem has our ML problem, like our model has a problem of overfitting. We can simply say this, right? So overfitting is a problem in a ML, like a model training concept, where the model is performing well on training data set, but it is not performing well on testing data set, right? And same way we have a problem, another problem that is called underfit concept, right? So model not performing well either on training dataset or on testing dataset. So it's like model not learn properly, right? So model or ML model, if I'm saying model na, so it's like ML model, model not trained, model not trained properly. So while training a model, we generally overcome with this problem underfit and overfit. but we have some sort of different techniques to overcome with this problem, right? We generally counter this kind of problem, overfitting problem and underfitting problem. Let me just show this visually, right? So overfit and underfit concept in machine learning, right? So overfit is like some sort of a data is, instead of just learning from its patterns, it just try to mug up or it just try to memorize the pattern. That is called overfitting. If we are getting, like if we are plotting the data set with respect to x and y axis, our model try to learn each and every data set. It try to like particularly fit or like so nice to the data set. It try to fit each and every value, and that leads to the overfitting concept, or like that leads to the overfitting problem, right? So it generally try to be nice with the data set. So this is the problem for our ML model, right? And the underfitting is like it's not trained properly, it's not learned the overall patterns and just randomly plot some lines or randomly calculated some boundaries. It's like an underfit problem. So what exactly we require? We required a balanced approach so that model generally perform well on training data set as well as on the testing data set, right? So we have different set of like concept to overcome with this issue, like underfitting concept or like overfitting concept. If we are getting the problem of underfitting, so we can train our model on different set of epochs, different set of random states. We can train our model multiple times to convert this underfitting or to eliminate this underfitting into the balance fit, right? But when it comes to overfit is like the overthinking. It's like model try to mug up or try to memorize each and every pattern. So it can perform well on training data set, but it will not perform well on testing data set. That is the major problem in the overfitting case, right? Let me show this practically. So this is something like this. This problem is called the Spiegel problem. Spiegel problem is like you try to connect with each and every dot. You have to miss out some points so that you can like particularly create a best fit line, right? So suppose we have some sort of data like this. The x-axis generally represent by the study hours and y-axis is like the marks. Okay, and let's just take the data set like this. We have some sort of scatter plot like this one. Okay, now we have to create the best fit line, right? You know that the model will try to randomly initialize the bias and the weights. The weights are like y is equals to mx plus c. Inside this equation you are already aware with that one, right? Y is equals to mx plus c, and m is just nothing, m is the slope, right? And c is called the intercept. And sometimes we also refer this m as weights, right? Instead of slope, we generally refer this equation as y is equals to wx, y is equals to w into x plus b, right? And here we are referring w as weights, right? So w is simply as the weight that we want to adjust during the training part, and b is just nothing, it's a bias, right? So instead of calling this slope or intercept, we generally refer this as weights and bias, right? Now model try to find out the two different set of values. The first one is called the weight and second one is the bias, right? During the training process, it will try to calculate two values. The first one is weights and second one is bias, right? So let's just randomly pick the bias value and it will, the weight is nothing, it's just like the slope or like the angle with respect to x-axis to the y-axis. It's like the derivative, right? So it will try to form a slope, and slope is like just changing the angle so that the line can be best fit and it can predict the best like prediction value, right? It will try to move like this one. Okay, we have this we generally pick this as a bias, right? Let's just move this along the y-axis so that it will try to fit the best possible way. Now suppose we have somehow picked this line, and let's just refer this as the best fit line, right? So the underfit problem could be like this. If I am getting the line something like this could lead to the problem of underfit. Underfit is like our line, our, our model not trained properly or our model not trained well, and that is the reason it's neither performing like it's not performing well on training data set as well as on the testing data set. That generally is the problem of a underfit, right? But when it comes to overfit problem na, so the underfit something like this, right? You can just simply say this as an underfit. So let me just quickly take a snap of this. And this is like the underfit problem. Underfit is like you are not able to find the best fit line. What about the overfit? So overfit is something like this. Let's just do one thing. Instead of taking a snap of this, let me just take a snap, this one. And this is like my underfit. Let me just create the line. This is the underfit scenario, right? And again, I'll plot the another scatter graph. And this problem is for overfit. Overfit, in this overfit, we try to connect with each and every dot. Instead of creating a line, now we try to connect with each and every dot, and that could lead to a problem. A model will not perform well on testing part. It can perform well on training part because we are not getting any like error on the training part, and that is a major problem in the overfitting case, right? We have to eliminate the overfit. See, we can simply eliminate the underfit problem by selecting the best feature or by reiterating or retraining the model, right? But when it comes to overfitting, the overfitting is like model are not particularly eliminating any noises. It try to capture each and every pattern, and this could lead to a problem in the practical scenario, right? So we have to avoid this overfitting, and we have some sort of different ML model that generally avoid all this overfitting concept, right? Now, what about the actual approach? So, actual approach should be balance fit. It should be neither on like the underfit side and nor on like overfit side. So, the balance fit could be like this. It will try to find the best fit line, and it is something like this. So, while we are creating any model, now we have to make sure our model, it should be not on both sides, neither on like underfitting side and on overfitting side. It should be always on the balance side, right? So this is for interview point of view. It's very important how to overcome with this overfitting problem and the underfitting problem, and what exactly do you understand by this overfitting and the underfitting. So let me just give a quick recap. Overfitting is like the model performing well on training part because it has already memorized each and every pattern. That is the reason it's performing well on training part, but not performing well on testing part, right? It cannot predict the best feature value, right? Now, what about underfit? Underfit is like the model is not performed well either on training part or as well as on testing part. It's like the mismatch of the or like some pattern already missed, right? Now, what about the balanced approach? So the balanced approach is like we have to somehow predict or like create a line or identify a best fit line so that it can be like useful in the best possible scenario. So that is called the balance fit, right? We generally have to create the balance fit ML model, right? So guys, I hope everyone is aware with that overfitting concept and the underfitting concept, right? Okay. Now let's just understand the how to eliminate underfit and overfit scenario. Okay. So we have two different techniques, and we generally refer this two different techniques as the regularization method. Guys, just listen to first. We have a technique, and that technique is called the regularization method. We will regularize our model so that our model generally perform well on training part as well as testing part, and that is called the balance fit, right? So we can use like the problem as the solution as L1 technique and the L2 technique, right? Let me just write the solutions. Solutions, the first solution that you can use, this is again can be asked in the interviews as well. Regularize, regularization technique, right? L1 and L2 technique. Okay. And second that we can generally use is called the cross validation. Okay. And third is like, see, why we are getting the overfitting? Because we are training our model again and again. That is the reason we are getting overfitting. So we can use the third technique that is generally used in the deep learning, not in ML, but we can use this, and the technique is called early stopping technique. Early stopping is like whenever we are about to get model as overfit model, we generally try to stop that training part. That is called early stopping, right? And if we just start this concept, because this concept remains same in ML as well as in the deep learning. So there is a technique in the deep learning that is called dropout layer. If anyone already aware with that, that concept is called the dropout layer. In this dropout, we generally try to drop drop the neuron which are not contributing that much enough. That is called the dropout layer, right? And fifth that we can use is the cross validation, so that okay, I have already used this one, right? The cross validation. So we generally write this cross validation as the CV, right? CV is like the cross validation. So we can use this, or you can do one thing. You can try multi-model approach, right? Multi-model concept, so that you are not getting the model either on like underfit side or like on the overfit side, right? So these are the solution, but technically we have to rely on this one, cross validation and early stopping, or like the dropout or like drop neuron, right? So let me just show you how to achieve this balance fit, right? So balance fit, balance fit is something, it performing well on both training as well as testing data set. Not only on testing data set, can it? We have some sort of unforeseen data set that are generally generated by the market, right? These are called unforeseen data sets, because while training our model, now we can only give the data set that we have. But what about the practical situation? We will not always give the data set, like we will get the data in the next day tomorrow, or like the day after tomorrow. So these data set are called unforeseen data set, where the model have never seen any pattern on this data set, right? So in the balance sheet, we try to create a model that generally perform well on both training as well as on the testing data set, right? Now, how to achieve that a balance fit approach? So we can use this technique, any of the technique, or like a regularization technique and the cross validation technique, right? Now let's just use this regularization technique. Okay, so why we are saying this regularization as L1 and L2 technique? Because we have two different ML model here, right? The L1 model is called regularization 1 model. We generally this we generally refer this as L1 model, or like L1 regularization model, and we have that model is called Lasso regression. Okay, see, you already are aware with linear regression, right? Linear regression, but whenever we are getting any problem like underfit or like overfit concept, generally related to overfit, right? Not underfit. So we have to optimize that model. And how to optimize that model? We have the technique. The technique is called the regularization technique, right? And L1 technique, let me just make it capital. L1 technique is like lasso regression. Okay. So this is a part of the linear regression, and this generally refer this as a lasso regression. This is the L1 technique, right? What it try? It will prevent model from overfitting. Okay, see, you know that whenever we are creating any linear regression model, na, we have to initialize the weight, right? And we know that the equation somehow like look like this: y is equals to, we are using the weight concept, right? And we have to calculate the error. Errors are like MAE error, MSE error, and RMSE error, right? MAE error, MSE error, and RMSE error. So let's just take example of MAE error. In this MAE error, we have to calculate the mean absolute error, right? Mean absolute error, right? So mean absolute error is somewhat like this. We have to calculate the absolute value, to just subtract the actual value minus predicted value, and then take a mean of it. I hope everyone is aware with that, right? It's like MAE is equals to mean of y actual, minus y predicted, and you have to make it modulus, so that you will always get the positive value. So let me just use the model like it. So it's like the mean of y actual minus y predicted. This is called the MA. Now what? How exactly this L1 try to regularize this model, right? So it will just do simply one thing. The L1 technique it try to more penalize the large weight, right? So it's like apply, let me just write this, apply more penalty to large miscalculation. Okay. See, it's like, let me just take an example. We have two candidates. The first candidate is like in nursery class, or like, let me just take it as LKG student. Okay. LKG student. Okay. That student committed one mistake, and it was like just broke some sort of like utensils or anything, right? Let's just take this example. Is like broken broke car window, right? Okay. So LKG student broke the car window. This is the mistake, right? Now let's just take another example. We have a 12th pass out candidate, and again he or she has committed the same mistake, right? Broke the car window, right? Now we want to penalize both of them, right? Now just let me know, will you use the same technique to penalize each of the candidates, the one who is studying in the LKG class and the second is like in the 12th class? I hope everyone is aware that because this 12th class pass out candidate is more mature, so you will definitely apply more penalty to this one rather than this one, right? So this L1 technique try to generalize the same thing. It will apply more penalty to the large miscalculation. Whatever the calculation that was wrong calculation, it will apply the more penalty to the miscalculation rather than the small one, right? So this L1 technique generally just penalize the large weights, right? So you can just simply write this as this L1 penalize the large weights is like large W value. Okay. So instead of this calculating using this MA, it has their different loss formula. Loss formula in L1 technique, and the loss formula become loss is equals to the original loss. Loss is like MAE, MSE, RMSE, pick any of the thing, right? Loss original and add additional add additional loss, right? So it's like additional loss. So we have a formula for that is called lambda and sum of all the weights, right? It's like lambda and sum of all the mod value of the weights, whatever the weights that we pick, right? So lambda is like the hyperparameter tuning we generally refer, right? So it's like we are just creating extra loss parameter, and it was like addition of previous loss plus some extra loss. So this lambda plus sum of weights is like extra loss. We are just giving extra loss because the model has committed some sort of mistake. So we are just more penalizing with the large race, right? So we in this LWL technique we'll try to minimize the overfitting issue, right? This L1 we generally use it for the minimizing of the overfitting issue, not for the underfitting. Just remember this, right? For underfitting technique, we have different solutions, not L1 and L2 technique, right? We always use this L1 and L2 technique to eliminate the overfitting issue, right? So it will just simply use new loss formula. If interviewer asks you now what do you understand by L1 technique, just simply say it will apply more penalty to the large miscalculation. It's like penalize the large weights, and it will use the new loss formula, the previous loss formula plus some sort of extra additional loss. It's like if someone have like missed their premium part or like the EMI part, so the company will apply some penalty now. So that is called the extra penalty, right? There is a candidate if they have missed their premium or like the EMI part, so the company will apply some penalty, right? That extra penalty is called the like new loss, and new loss generally try to minimize the overfit issue, right? So candidate, you can use this L1 technique, and instead of calling this L1 na, this the main name is called the Lasso regression, right? So we will use this Lasso regression technique, right? Now let's just understand the another technique that is called the L2 technique, right? So you can just simply go to Google and simply write this L1 and L2 regularization, right? So here is very smallest like short definition that you can refer: prevent machine learning from overfitting. And you know that by adding what? By adding penalty term to the loss function. And loss function is whatever the loss function we'll use, like mean absolute error, mean squared error, and root mean square error. So that the simpler model of like the simple weights can be like eliminated, and the weights that having the large or like the miscalculation, it will be penalized more. So you are just adding the penalty term, and the formula look like this one. L1 is called the Lasso regression, and the L2 is called the ridge regression, right? So let me just show you the formula of L1 regularization versus L2 regularization. Go to this, and this is the lambda formula that you can refer, right? Like this one, okay? Yeah, this is the actual formula, right? So we are just adding some, see, this is the previous weight, right? And we are just adding some extra lambda parameter with the some sort of weight assigned, right? This is called L1 technique. Now let's just understand the L2 technique. This L2 technique, we refer this L2 technique is as the regularization technique 2. REGULARI, yeah, regularization technique 2, and we refer this as a ridge regression, right? So whenever anyone talk you about the regression problem, na, so you can just simply refer. We have three different set of regression. The first one is like the linear regression, but if we are getting the overfitting concept or like overfitting issue, so we can use the two different techniques. The first one is L1 technique, and second one is L2 technique. The L1 is like the lasso regression technique, and L2 is like the ridge regression. Okay, so ridge regression also do the same thing. It's like the it prevents it from overfitting, but we have some sort of different formula. Instead of using this lambda and sum, we generally square both the value, right? Here we are getting the same. See, this is the loss, and in this ridge regression, we just simply, instead of directly picking this modulus value of the weight, we just simply make it squared, right? So it's like, let me just call the same thing. The new loss will become previous loss plus lambda value, and not directly summing up this value, you have to make it square. So it's like w raised to the power 2, right? And this is called the new loss function inside this regularization technique, right? So what it will try to just conclude, whenever you can just say, whenever you are getting multicollinearity problem, if you are getting multicollinearity problem, it's like, what is multicollinearity? Where one feature is dependent on other features. In the practical situation, we want feature to be dependent on the like target to be dependent on the feature. But sometimes we, or like not the sometime, in the practically we generally get the feature is dependent on the feature. So that generally refers this as a multicollinearity. If we are getting multicollinearity problem now, so we can get the overfitting issue, right? And in that case, we can use the L2 technique, right? So one feature is dependent on other features, right? So you can use this L2 technique, right? What is the formula for the loss one? So the loss will become original loss plus lambda, and instead of directly calling the modulus value of all the sum of weights, you are just adding the square, or you are just keeping it square value, right? So you can use it for the overfitting case. So it eliminates the overfitting issue, right? So we generally refer this as a, we have a two different technique to to like remove the overfitting issue. The first one is called the L1 technique, and second one is called the L2 technique, right? But sometimes interviewer generally ask you one more thing. Suppose we don't want to use L1 and L2 technique. So is there any another technique that we can use? Yes, we have another technique. The third technique is called the elastic net. And elastic net is very easy. It's like the combination of both L1 plus L2 technique. So you can just simply write this as combination of both L1 plus L2 technique. And that becomes the elastic net. So you can just go and Google what is elastic net regularization. So it's like the combination of if it is a linear regression that combines both lasso and ridge regression, and it will apply penalties to enhance the prediction accuracy. See, this is a very basic definition, right? So you are just simply using, not just simply using the L1 and L2, you are using L1 and L2 together, and that becomes the elastic net. So we have we have three different techniques of regularization. Regularization, the first one is called the L1 technique, second one is like the L2 technique, and third one becomes the elastic net. And elastic net is nothing, just combination of both L1 and L2, right? So the loss formula become, can you just let me know how to identify the loss of this one? Very easy, right? So just simply copy of any of the loss, and the formula become loss original plus the L1 weight loss. It's like the lambda sum of something, this extra lambda, and plus you can use this one, right? Lambda and lambda multiply sum of square of both the, like all the weights. So the new formula will become like this. Okay. Now what about this lambda? So this will be because the lambda of L1 now, so you can just say this as lambda of L1 or lambda of L2. So the final formula will become new loss is equals to previous loss or like original loss plus lambda 1 or like hyperparameter of L1 technique plus sum of all the weights that has been assigned, then plus lambda 2 of L2 technique, and then sum of all the weight assigned and with their square value. And that is the main formula of this new loss in this elastic net concept candidate. I hope everyone is getting my point, guys. Guys, are you getting now? Candidate, is there any issue or like questions with this one? Different techniques of regularization. The first one is called L1 technique, second one is called L2 technique, third one is called the elastic net. Elastic net is just, see, this can be asked in the interview, right? What are different regularization techniques? So you can just let them know we have three different regularization techniques, L1, L2, and elastic net. L1 and L2 both try to minimize the overfitting issue, not the underfit one. Just understand this thing, right? Elastic net is a combination of both L1 and L2 technique. Now, how to practically use this, right? So we have already the data set that was like the some sort of Canada per capita price income prediction, like sort of like this. Let me just take a reference of this one so that we can practically apply the things, right? Canada per capita income Kaggle, and the data set is like this. Canada per capita income Kaggle. You can just download this. We have already used this one, candidate, right? And how to implement the L1 and L2 and both L1 plus L2 are like elastic technique, right? So let me just run this. You can take a reference of the previous notebook, right? Instead of writing this, let me just go and open the previous classification problem using ML, and I'll just quickly copy each module. I hope everyone is already aware with that, right? We don't want to write it manually again and again. Let me just copy all the parts. Okay, and what I want, I just quickly want, I don't want to use the logistic regression because the problem right now we have is the linear regression, right? So let me just remove this, and we can use this error, right? Mean square error, mean absolute error, root mean square error, because the problem is related to the regression part, right? Now what about how to import the L1 technique, L2 technique, and the regularization technique? So all these are fall under this linear model concept. So you can just call this from sklearn.linear model, import linear regression, and you can just write this as like ridge regression and lasso. So just simply write this as lasso, and then second is as ridge, and third is as elastic net, right? Elastic net. So we can simply call this from sklearn.linear model, import linear regression, the first that generally gives the balance fit. But if we are getting the overfit, this can be removed by this L1 technique. Second is L2 technique, and third one is L1 plus L2 technique, right? Candidate, everyone, is there any doubt related to this? Now let me just quickly convert the data into X and Y part. Okay, so just call this os dot list dir and paste the path that we have. Use the zero to just give the file name or like Canada, something like this, and quickly just store this inside the file name. Create a file path. I hope everyone is aware with that, right? That we have used this code multiple times, right? You can just simply do one thing, add the file path, pick the like the previous path we have, then use the concatenation approach, plus use the forward slash, and then use the file name, and then you can quickly read out this data pd.read underscore csv, and then followed by the file path, right? Let me just run this. We have this data set here and Canada, some sort of like this per capita. Okay. Now let me just run this df.sample. And now we have this data set. We can quickly turn out this data set into X and Y. X is like df double square bracket of this Y, because we have to give the data frame in the X part, and the Y is something like this df. Let me keep it unindent df or dot. You can use this one, right? Uh, the per capita. You can use the dot approach as well, right? So we have converted the data set into X and Y. Now we are going to use the L1 technique, L2 technique, elastic net technique, and the linear regression concept also. Okay. So before directly creating the model, now let's just quickly understand the boosting part. Okay, guys, before directly starting this boosting part, just let me know in the message area. Everyone getting my point? What is L1 technique and L2 technique and elastic net, guys? Is there any doubt or like question related to L1 and L2 technique? Let me just start the boosting part, and then we'll create the final model by running a for loop where we will use the multi-model approach. Candidates, just let me know in the message area. Is there any doubt related to regularization technique L1, L2, and the elastic technique, guys? Purti, Sneha, Tejaswini, and the rest candidates. Is there any question related to this? So interview generally asks you the loss formula. So the loss formula you can just simply refer this as, right. And if you just want to make it more generic definition, so you are just applying more penalty to the like the higher the weight assigned, because it has committed the like major mistake. It's like both candidates broken the window, but you are just penalizing the 12 pass out candidate because that particular candidate is the more mature one, and you are just applying the same loss formula to the same weight candidate, right? So let's just quickly start the boosting part, right? We have already understand the we have already performed the bagging part, right? Now, what about the technique? So, in this boosting technique, let me just quickly give you the recap. Boosting is like the bootstrap aggregation, some sort of, we are just boosting the data, right? We are just boosting the model from weak learner to the like smart learner, or like you can say the strong learner, right? So in the boosting technique, we have different boosting technique, right? First, we will take a sample from the data set. We'll create the first model. That first model is called the weak learner. Okay, this weak learner try to predict some values. Okay, and it will also do some like calculation and try to learn from the data, but there might be chances the model not perform well. So there are some sort of misclassification or like miscalculation, that is called error. Now whatever the error or like whatever the wrong classification we'll get, we'll try to again boost the same model with the data set. Like due to which we are getting the errors, we'll again boost the model, and in the next step we will again boost the model, and that weak learner converted directly into the strong learner. Why we are calling this boosting? Because in each and every stage we are boosting the model to get more accuracy, to get more accurate result, or not to become overfit, right? We have to eliminate the overfit concept as well, right? And why we are referring this as a sequential? Because one model building is connected with the another model building, but in the bagging technique we have to run model parallelly, right, where each individual model is responsible for their individual prediction, right? Okay, you can again take a reference of this image to explain bagging and boosting, right? Let me just quickly paste this. Okay. Now we have different set of boosting techniques. How to use first a list of boosting techniques. The first one is like the ADA boosting, or you can just start with the gradient boosting. It's like the gradient boosting technique. Second one is like the ADA boost The ADA generally refer this here as a adaptive boosting. Okay, adaptive boosting. The third one is called the light GBM. The light GBM is like light means fast. Okay, light means fast here. Light is not just like the light speed of light, some sort of light generally is like for light means fast. And GBM is like gradient boosting. It is like fast gradient boosting technique. You can just say light GBM, right? Fast gradient boosting, gradient boosting. And M is like machine. Okay. So the fourth boosting technique that we have is called the XG boosting. And X is like the extreme here, and G is like the gradient, right? So it will become extreme gradient boosting, right? So the finally it is extreme gradient boosting. Now you know that we are getting gradient boosting again and again, right? Here we are getting gradient boosting, and this light GBM we are also getting gradient boosting. Again we are like in this extreme gradient boosting or like XG boost we are again getting gradient boosting. Okay. The fifth one is like is the cat boost, and we generally use this for categorical boosting. Okay. So mainly we have five different types of boosting techniques. So just quickly copy this, go to Google, list of boosting techniques, you'll get the list of all this one, right? Adaptive boosting, gradient boosting, XG boosting, light GBM, and the CAD boosting. We have some sort of like histogram boosting as well, or like other different set of boosters, right? But we generally refer this as ADA boosting, gradient boosting, extreme gradient, light GBM, and CAD boosting, right? Let's just quickly understand the each individual boosting one by one, right? Okay. So we are going to understand first the gradient boosting technique. What is gradient boosting technique? In this gradient boosting, now we will use the concept of gradient descent concept to minimize the error or to identify the best fit value, right? So here we will use the gradient descent concept to minimize the loss, minimize the loss. And we know that the loss is something like we generally refer this loss as residuals, right? We can refer loss as loss, we can refer loss as cost, and all are like y actual, y actual, not p actual, it's like y actual minus y predicted. These are called loss, right? And how to just quickly understand here what is loss? It's like the difference between the actual value and the predicted value, that is called loss, right? So this one is like my actual value, this black one is the actual value, and you are getting the prediction some sort of like this. So the difference between this black one and the red one is called the loss. Okay, you can refer this like this. This is called loss or like error one. Same way you are getting loss two is like error two. Okay, let me just take this predicted value as like this one, and the error two will become, see, it's not I'm like just taking this as error two. This is like error one, this one is error two, error three, error four, right? Just for example, we are referring this as a error two. So it's like actual value minus predicted value, and all this actual value and predicted value is called the loss, or we can refer this loss as a residuals or like a cost value as well, right? So you can just say this, or you can take a image reference like this residual plot. We have the residual plot inside the ML where it will try to just give the difference between the loss value, right? This is like the residual plot. Okay, whatever the loss we are getting, we can simply plot the residuals, right? This one where each and every value or like each and every difference will be plotted by some sort of like this. Okay, these are called the outliers, and outliers are like the misclassification, and the model is not able to quickly understand the pattern, right? These are my highly predicted loss, right? So in the gradient boosting, we will use the gradient descent concept to minimize the loss. Now, let's just quickly understand the what is gradient descent. I hope everyone is already aware with the gradient descent concept in the machine learning, right? The gradient descent is a technique. It will try to optimize or to find the best weight value or best bias value to just quickly minimize the loss or to get the like optimal value of the weight and the bias. Okay, let me just explain this more practically, right, so that you can easily understand. Okay, so guys, we know that we have the formula of equation of line that is called y is equals to mx plus c. Y is equals to mx plus c. And you know that we can refer this formula as y is equals to w into x plus b as well, right? So you know that the predicted y is just nothing, it's a predicted value. Okay. So what is y? Y becomes the predicted value, y predicted. So the y predicted is based on the weights. Y predicted based on the weights multiply by the x. X is like the input. And then plus with the bias. Bias is like the intercept, right? So the generic equation is like y pred is equals to weight dot x plus bias, right? Now you know that the loss is nothing. Loss are like you can take any loss, mean absolute, mean square, and root mean square. Let me just make it more generic. So loss is like y actual minus y predicted. So it's like y actual minus y predicted. And you know that we have a formula of y actual and y predicted. If I just taking example of MAE, so MA is like, let me just write this. MA is like 1 by n. 1 by n is like we are taking mean summation of modulus of y actual, y I. I hope everyone is already aware with this formula. And y cap. Y cap is like the y predicted value, and you have to take a mod value of all this one. It's like the mean absolute error, right, candidate? Now, instead of just writing this as a y cap, I will use this y cap prediction like the formula like this one. Y pred is like weight into x plus bias. So I can just simply write the formula again, formula like this. The loss is like loss is equals to y actual minus, instead of writing this y predicted, I will use the weights multiply x or plus b. Can I say this, candidate? The loss will become like this y actual minus weight into x plus b, right? Now I know that y the loss is completely dependent on the weight and the bias. Y actual we will get the y actual from the data set. We will get the y like x value from the data set itself. It is like the input data. But what we have to calculate? We have to calculate the weight value and the bias value. So I can just simply say that loss is loss is dependent on weight and bias. Can I say this? So loss is dependent on weight and bias. If I say this, candidate, so it becomes something like this. Loss function is like some sort of dependency with the weights and bias, right? So loss function is completely depends upon the weights and the bias. So let me just draw this with the help of loss and weight and then loss and bias, right? We have two different Cartesian. The first one is for loss and weight and second one is for loss and bias, right? We have loss here and loss with respect to W. And again, we have loss here and loss with respect to bias, right? Now, what we want, class? We know that loss is completely dependent upon weight and bias now. So, loss is a function. And if you want to plot the function, so it will something look like this, okay? This one and that one, okay? Now, what we want, here we are getting the increasing in the loss value, same as it is the increasing in the weight value. Same followed by the bias value and followed by the loss value, right? What we want, candidate? We want the minimized loss, right? The loss, let me just make it more clear like this and like this one. We want to minimize the loss, candidate, and we know that how to minimize the loss. If I just move like this forward, so my loss is somehow decreasing. It's like this, okay? and we are getting the minimized loss here. That is called my global minima. It's like my global minima. Okay. We have to calculate this global minima, and if you want to calculate this global minima, Vana, you already know the concept of domain range, domain and range, and domain and range is like you have to calculate the derivative, right? Derivative of derivative of loss with respect to weight, and same as it is, you have to calculate the derivative of loss with respect to bias, right? Then you can probably calculate the global minima. We refer this as the global minima. This one is the global minima, and that one is like the global maxima. This one is like your global maxima value. See, it's like, not like the maxima that we want, because global maximum is the infinity, right? But we have the global minima. These are like the global maxima. But what we want to calculate the global minima value, right? So let me just write this global minima, and the global minima is something like this, where the function getting the minimum value. This one is the global minima, and this one is also the global minima, right? At this point, function is getting the minimum loss. It's not like the like zero loss. We are getting the minimum loss. The minimum loss could be anything, right? But at this overall function curve, we are getting the minimum loss here. That is called global minima, and that one is also called the global minima. And if you want to just calculate the weight with respect to the global minima of loss with respect to weight and loss with respect to bias, so somehow we have to minimize our loss in a generic way so that we can uh, finally end up with the global minima value. So what exactly the function will try to do, it will try to just simply step descent to just close to the global minima. It will start from some sort of upper value where we are getting some maximum loss. Then it will try to go descent and where we are getting the global minima. Okay. And that the descent value is called the learning rate. The more you will go, the more there are chances you can skip the. See, if you just try to descend very quickly, very fast, so there might be chances you can simply skip out all the global minima value, right? This can be the chances, right? So it is recommended to just step downward with the very lowest possible value. That is called the learning rate, right? So instead of directly jumping with the higher values, we will we will generally pick this as the lowest one or like the lowest learning rate. So you will start some sort of like this. You will just move downward to just close to the global minima like this one, and all these jumping values called the l- learning rate, right? And once you reach this global minima, then you will stop the iteration. Once you will reach the global minima, then you will stop the iteration. And this stepping descent is called the gradient descent concept candidate in the machine learning. You have to optimize the loss by calculating the weight and the bias. So you know that the stepping descent is called the learning rate, and you have this parameter that is called learning rate, and we generally pick the value of learning rate is like 0.001 or 0.001. The lesser the value, the lesser the step that it will take. More the value, more step it will take. And if you increase the learning rate, the chances of getting you can skip this global minima becomes more, right? If you are increasing the learning rate value, the chances of skipping this global minima becomes more, right? So you have to keep the learning rate at very lowest level, right? So guys, in this way, this loss will try to optimize with respect to weight, loss will try to optimize with respect to bias, and this concept is called the gradient descent concept, right? This is the gradient descent concept. The gradient is like calculation of the derivative, and the descent is like the step that we are taking towards the descent or like the declining. It's like the convergence, okay? And that becomes the gradient descent concept. This same gradient descent we pick or like we refer the same gradient descent technique in the gradient boosting technique, where the new model will be like convergence of the previous model. It's like we'll try to eliminate the loss from the previous model, and that becomes the gradient boosting technique. Okay, so you can just refer this as the gradient boosting gradient boosting algorithm, and you can just take a reference of this image like this one. Okay, where we are eliminating where we are eliminating the miscalculation, or we just try to minimize the error with increasing in the number of iterations, right? This one is the perfect classification, but somehow we got the misclassification. Then in the next iteration, we try to minimize the losses. In the same, like in the again next iteration, we try to minimize the loss and followed by the descent approach. So it's like the gradient descent boosting concept where we'll try to minimize the loss, where the next model will be more accurate than the previous model. And that is the reason we are referring this as a boosting technique, where the weak learner turn up with the like strong learner, and then finally the strongest learner that we will get at the output of the, or like at the end of this boosting algorithm, right? So class, in this boosting technique, we generally refer this as the gradient descent concept, where we try to minimize the loss with some sort of the learning rate parameter, right? I hope everyone is getting my point, guys. Guys, are you getting my point? Everyone, just write here in the message box. Are you getting my point, candidate? Everyone, Sneha, Tejaswini, Purti, and the rest candidates. Just quickly let me know in the message area. In the gradient descent technique, we generally try to minimize the loss, and we try to reiterate the model so that the loss generally at the minimum, like the minimum level, right? So how to import this gradient descent? You know that simply because all these are part of a boosting technique now. So you have to use the ensemble technique. So you can just simply refer this from sklearn dot ensemble learning. Just quickly call this as gradient boosting, right? You will just run this gradient boosting regressor. You can use this gradient boosting for the regression problem as well as for the classification problem. It's like the gradient boosting regressor and gradient boosting classifier, right? Now the second model is called the ADA boosting. ADA boosting is like the adaptive boosting. Adaptive boosting is some sort of like we are adapting something. Here in this previous scenario, guys, you can simply refer this. We are particularly picking up the value of a fixed learning rate, right? Then if you fix your learning rate, so the learning will become like gradually. It will not like improve exponentially, right? So it's like something linear learning rate, right? So what we want, instead of particularly fixing the learning rate, we just make learning rate adaptive. We'll just simply make learning rate. Let me just correct this. LEARNING. We just simply keep learning rate as adaptive. Adaptive means if it will got a chance to improve the learning rate, so it will try to adapt the learning rate and increase or decrease the learning rate based on the loss, right? If we are getting the loss, so it will try to decrease the learning rate. If we are getting more loss, so it will try to increase the learning rate. No, if we are getting the more loss, it will try to decrease the learning rate. But if we are getting the less rate, less loss, so it will try to reduce the learning loss. So we are adapting the learning. We are adapting the learning rate as per the losses, right? So it's like adaptation of adaptive learning rate, or like adjustment of weights at adaptive level, and that becomes the ADA boosting technique. Okay, so in this ADA boosting technique, we generally try to keep our model as adaptive so that it can learn from their mistakes, and keep it try to understand the like previous mistake and just try to eliminate or like minimize the mistakes, right? And that becomes as adaptive boosting. Okay, now how to call this adaptive boosting? So just simply go to this from sklearn.ensemble, and you can again import the ADA boosting, right? ADA boosting regressor. Okay. Now, what about the light GBM boosting? We generally refer the light GBM boosting when we have when we have a problem of a very light or like a fast data set. If we are getting very fast data set, if we are getting if we are getting very fast data set, or like very huge amount of data set, then we will use this light GBM. So the light generally refer this as a fast or for complex data set, right? and you can simply like import this, but you have to install this LightGBM first. So you can refer this if install LightGBM. Okay, in the same way you have to import the like install the XGBoost as well, right? So you can just run this pip install LightGBM, just copy this pip install LightGBM and quickly run this pip install LightGBM, then you can probably use this, right? Okay. So in this LightGBM now candidate, there is a concept of like kind of like leaf tree kind of structure in this light GBM concept, and it is generally work on the like it generally work faster on the large data set. So whenever you are getting the large data set now, so it is recommended to use light GBM concept, right, for the boosting technique. Okay, now we have installed installed this light GBM. How to import this from light GBM? You can just write this as light GBM regressor, right? Just wait for a while. Yeah, light GBM regressor. Where is the light GBM LGBM? Write this LGBM regressor. You will get the LGBM regressor, right? In this way, you can import this, right, candidate? And you know that we have a concept of tree here, right? So you have to give the an estimator. An estimator is nothing, just like the tree structure, right? So you can just simply define the by default tree structure is like the 100 kind of decision tree, right? So you can use this light GBM, right? Now, what about the XGBoost? XGBoost is like for the extreme gradient boosting. You generally, if you want to use both L1 and L2 technique together, so you can use this XGBoost, right? Instead of calling annual L1 and L2 technique, if you use this XGBoost technique now, the model will already perform the L1 and L2 technique, right? So you have to again quickly install this pip install XGBoost. Go to this, take a copy of this one and run this, right? Now you can import this from XGBoost. You can import XG regressor and XG classifier, right? XG boosting RF like the regressor, or you can use it for the classifier as well as, right? Whenever it is like recommended to use L1 and L2 technique, then you can use the boosting like the extreme gradient boosting. It generally, let me just write this, XG boosting, it default use regularization technique. Okay, it runs parallelly, right? It runs parallelly, and if you are getting the complex data set useful for complex data set or huge data set, right? And you can use this XGBoost random forest classifier and XG as well as the regressor part as well. Use this one, right? XGBoost regressor. Okay, perfect. Not to use this one, right? XGB classifier and XGB regressor. Okay. Now, what about the last one, candidate? The last one is like the CatBoost. CatBoost is generally useful for the categorical boosting, right? We know that if we are getting any categorical data, right, we have to convert the categorical categorical or like textual data to numerical now. So what it will try to do, it will perform that concept automatically instead of using one hot encoding, right? One hot encoding or like get dummies technique or any map technique to convert textual to numerical. We can use the categorical boosting. So categorical boosting is like the combination of it all. It by default handles categorical data. You can just simply write this automatically automatically handles categorical data transformation, right? And boosting part is one of them. Perfect, candidate. So we can use this cat boost, right? And how to import this? Again, you have to install this. It is called cat boost. You can just write this pip install CatBoost, okay, and just copy this pip install CatBoost and just from CatBoost from CatBoost. Okay, I'm not getting the suggestion. Yeah, from CatBoost import CatBoost regressor and CatBoost classifier, right? So you can use this one, right, candidate? Why we are using this multiple model approach? Because you have to perform one sort of calculation here, right? We have used this gradient boosting regressor, ADA boosting regressor, LightGBM regressor, XGB regressor, and CatBoost regressor. But right now it is not required because we don't have any categorical data. But what you have to do, because we have already converted our data set into X and Y, so you have to use the all model approach. And you can just write this as the first one is like the linear regression, okay. Second one is like the uh, lasso regression. You have to use this concept, okay. Let me just summarize this one. The third one is like the rich concept. Fourth one is like the AdaBoost. You have to create a list of this one. The fifth one is like the XGBoost, and the sixth one is like the gradient boosting. Okay, gradient boost regressor. And seven one is like the elastic net. Okay, elastic net sort of like this elastic net, right? And then this becomes the all model approach. Then you will run the for loop and create your model, and then you will identify which model performing well, right? So let's just keep this for today right now, and we'll start the multi-model approach tomorrow. I hope this is enough for the today candidate, right? So we have imported all the modules in the tomorrow class. This is again your homework. If you want to run a for loop, you can run or like create a multi-model. If you don't do this, I'll like particularly do this in the next class to pick the same data set. We will create the multi-model approach, followed by the linear lasso ridge and elastic net, and then we'll try to evaluate the model. And whatever the best model it is, then we'll try to save the model, right? So this is enough for the today candidate. Is there any doubt or like question? Can you just let me know, or shall we close this session? Right, we have already closed the 9 minutes extra. So, is there any questions or doubt? Tejaswini, Sneha, Santala, Spurti, and the rest candidate. Okay, so I have already shared this notebook, right? Let me just quickly download this and upload over the GitHub. You can take a reference from the GitHub, then you can practice it parallelly, right? So let me just quickly stop the recording. Let's just connect tomorrow, candidate, right? Wish you all the best.